All right, in this video, we are going to talk about section 3.1 on Eulerian graphs. All right, so first off, in this section, we're going to deal with multigraphs and pseudographs. And remember, the terminology is non-standard depending on what source you're looking at. So I am going with the terminology that's in our book. Okay. So when I say graph, I mean just a simple graph, no loops or multiple edges between vertices are allowed. So, and then if you're going to allow two vertices to be joined by more than one edge, that's called a multigraph. And you can see here's an example of a multigraph here. And then a pseudograph is a multigraph that allows loops in it. Okay. So an edge from a vertex to itself. All right, so that's what we're going to be dealing with in this section. So just to remind you, again, the terminology is going to be different if you look in other sources. All right, so this topic that we're studying here basically goes all the way back to the very beginnings of graph theory. And that is the Königsberg bridge problem. So in the city of Königsberg, Prussia, and now that's in Kaliningrad, Russia. So you can see here is where it's located. And and I actually didn't realize that Russia had this small territory over here that's not really adjacent to the part itself. So, but anyway, if you look at this, the city, right? Then it's this little island right here. There's the river, and the river kind of splits apart in the delta, like it does when it comes out to wash out into the ocean, and so this river kind of splits apart, and you had this island here and this island here that's formed by that. So the question was it used to look like this. This is the map, I think, from the original publication. And there used to be 7 bridges. You can see it's a lot different than that now. It's just kind of one big bridge. I guess you can kind of think of that as 2 different ones, but it definitely looks different now than it did back then. So in that time, in the small island, there was 4 bridges, and then the bigger island, there's 2 bridges here, and then there's a bridge joining the 2 islands together right here. I think that one is still there. I think these 2 are possibly the ones that are missing. So the question was, beginning at any bridge, is it possible to cross all 7 bridges exactly once and return to the starting point? And so Euler proved that it was impossible to do that in 1736. And so that was basically the beginnings of graph theory. And so you can see sort of this problem translated into a graph here. So here, and this I think again comes from the original solution of this. You can call these land masses, give them labels. That's what Euler did: A, B, C, and D. Right, and then the bridges are sort of represented by the edges in the graph like this. Okay, and so that's what's you generate a multigraph like this, and this is actually the multigraph that it had in the very beginning as well. So this multigraph right here. All right, and then Euler was able to prove that that you couldn't do that. So you couldn't walk across each bridge exactly once and cross all bridges. Okay. So to get started in that direction, we will talk about walks. And since we are talking about pseudographs now, then we have to be, our definition has to expand a little bit because of the fact that we have multiple edges between vertices. So a walk in a pseudograph G is an alternating sequence of vertices and edges with the property that every edge is incident with the vertices that are prior to it in the sequence and that follow it directly follow it in the sequence. Okay, so for instance here we have that edge E1 would have to be incident with vertex A1 and vertex A2 and so on and so forth through the sequence. And the two vertices can't be equal to each other unless you have the edges a loop, and then that's okay. If there's a typo here, this should be A1. If A1 is not equal to A sub n, then the walk is called an open walk. So in other words, the beginning vertex and the ending vertex are not the same. If A sub 1 is equal to A sub n, then the walk is called a closed walk. So in other words, the walk begins and ends at the same place. And then the length of the walk is the number of edges that are in the walk. And so in this definition, there is nothing that says that prohibits vertices and edges from being repeated. All right, so here I have an open walk example, and so let's take a look at that. All right, so here we start with A, and then we go to B through the edge A, and then from B to C we use the edge C, and then we go from C back to B via the edge D, from B to C using the edge C, so there we used edge C again, and then from vertex C to vertex D using edge F, and then from vertex D to vertex D using the loop H, and then again, and then we go from vertex D to vertex B using edge G, like so. And so that's an example of a walk, an open walk, since we started at A and we ended at B. Okay. All right, next up is a closed walk. Let's take a look at an example of that. And all right, so here again, we're going to start at vertex A, and then from vertex A, we're going to go to vertex B using edge A, then from vertex B to vertex C using edge C, then from vertex C to vertex B using edge D, then from vertex B to vertex C using edge C again, then from vertex C to vertex D using edge F, and then twice around this loop again, then from vertex D to vertex B using edge G, and then finally from vertex B back to vertex A, which is where we started from, using edge A again. So that's an example of a closed walk because of the fact that we started at vertex A and ended at vertex A as well. Okay, so next up is a trail, and you'll notice that these conditions get a little bit more restrictive as we go on. So a trail in a pseudograph G is a walk in G with the property that no edge is repeated. Okay, so let's take a look at a trail, and the main difference, right, is we can't repeat edges. All right, so starting again at vertex A, we are going to go to vertex B using edge A, and then from B to C, right, using edge C, then from vertex C back to vertex D using edge D, okay, then from B to A using B, edge B, then from vertex A to vertex D using edge E, then from vertex D to vertex D using the loop H, and then from vertex D to vertex C using the edge F over here. Okay, so notice that we did not use any edge more than once. So there's no repeated edges, so that would be a trail. Oops. All right, next up is a path. So a path in a pseudograph G is a trail in which G with the property that no vertex is repeated. So here we cannot repeat any edges, we can't repeat any vertices. All right, so our path here, we're going to start at A, and we're going to go from vertex A to vertex B using edge A, then from vertex B to vertex C using edge C, then from vertex C to vertex D using edge D. Okay, so there is a path. This definition if we are just looking at a graph, what we call a graph, what other books might call a simple graph, then this definition agrees with that definition. That we talked about before. All right, the next definition is a circuit. So a circuit, and it's also a closed trail, is a trail whose endpoints are the same vertex. So it is a trail, so no edges can be repeated, and the starting vertex is the same as the ending vertex. So let's take a look at that. All right, so here we're going to start at vertex A, and we're going to go to vertex B using edge A. Then we're going to go to vertex C using edge C. Then from C to D using edge F. Then from D to D using the loop H. Then from vertex D to vertex B using edge G. And then from vertex B to vertex A using edge B. All right. And so there we go. That is a circuit, right? So it's a trail, so no edges repeated. And we started, wherever we started is where we wind up at the end. Okay? So that is a circuit. All right, and next up is a cycle, and a cycle, also called a closed path, is a path whose endpoints are the same vertex. So it's a path that we're talking about, so no edges and no vertices repeated, and the other than the beginning and end vertex, right? So, all right, let's take a look at that. All right, so here we're going to start at vertex A. So we're going to go to B via edge A, then from vertex B to vertex C using edge C, then from vertex C to vertex D using edge F, and then from D to A, vertex D to vertex A using edge E, like so. All right, so there is a cycle. All right. So that brings us to this part about the shortest cycles. Remember before when we were dealing with graphs, the shortest possible cycle that you could have was of length 3, and that's called a triangle. You can see an example of that here in green. Okay, but in a pseudograph, it is possible to have a cycle of length 1, and that's called a loop, like so, and a cycle of length 2, that's called a loon. All right, so here in blue you can see an example of a loon there as well. So that's an important difference between cycles in pseudographs and then cycles in graphs or simple graphs, however you want to call them. Okay. Also, one difference that we'll have about the degree of a vertex, it's the degree of a vertex V in a pseudograph is the number of edges incident with V, so that's the same as before. But the main difference here when we're talking about pseudographs is that the loops are counted twice. Okay, so got to count those twice when we're talking about degree, and that's important. Okay, that brings us to the idea of an Eulerian circuit. An Eulerian circuit is a pseudograph G, or in a pseudograph G is a circuit that contains every edge of G. All right. So just as an example of that, remember in a circuit we can use the vertices more than once. Okay. So let's take a look at that. All right, so here we're going to start at A. And we're going to go from vertex A to vertex B using edge A, and then from vertex B to vertex C using edge C, from vertex C to vertex D using edge F, then from D to itself using edge H, or the loop H rather, same thing, but to be more specific, it's a loop, right? Then from vertex D, we're going to go back to vertex A using edge E. Then from vertex A to vertex C using edge G. Then from vertex C to vertex B using edge D. And then from vertex B to vertex A using edge B. All right, so this is an example of an Eulerian circuit, right? We started at vertex A, we ended at vertex A, right? So that makes it a closed, right? And we didn't use any edge more than once. That makes it a trail, right? A closed trail is a circuit. Right, and so we have a circuit here, and that circuit contains every edge of G. Right, we used up every edge when we did this. So this is an Eulerian circuit, as opposed to the previous example. Right, when we did a circuit, I don't think we used every edge, but I already closed that out, which I probably shouldn't have, but that's okay. All right, so this is an Eulerian circuit. Okay, so starting with the theorems that we're going to talk about in this section, and in this video I'm just going to give an overview, and then I will go back and post proofs in just videos of themselves, so the formal proofs. I just think that it flows a little bit better like that. Okay, so if a pseudograph G has an Eulerian circuit, then G is connected and the degree of every vertex is even. Okay, so the thing is that with an Eulerian circuit, if you have an odd degree vertex, right? First off, if it's connected, right? If it's not connected, if you have an Eulerian circuit, right? You got a circuit that goes through every edge, right? And therefore, it's going to go through it every vertex at least once, right? So it has to be connected. That means you can find a path from one vertex to the other, right? And the degree of every vertex has to be even. So the idea behind that, right, is that if you if you have an odd degree vertex, right, or an even degree vertex, every time you come into the vertex, then you're going to be able to leave the vertex if the degree is even. So let me pull this up so I can draw on it a little bit. So let's say it has degree 4. And again, this is just an overview, it's just kind of the idea behind what's going on. So you have your circuit, it's going to come in here, right, into the vertex. And since it's only been into this vertex once, right, there's going to be an edge that it's going to leave on. So the circuit's going to come through the vertex like this, and it's going to leave and go someplace else around there. And so then it's going to come back in at some point eventually. And so notice when it's coming in, it's used up an odd number of the edges incident with the vertex, right? So when it came in, it used 1. It left, it was 2. It came in again, it's going to have used up 3 of the edges that are incident with the vertex. And because there's another one, it's going to be able to leave. So if you have an even degree vertex, every time it enters, it's going to be able to leave and continue on that path or that circuit. Whereas if you have, say, an odd degree, right, and it comes in like this, and it leaves, say, and then comes back, goes back around the graph someplace else. Then the next time it comes back in, well, then it's not going to have any other edges, right, to leave on, and so that's going to kind of kill off the circuit at that point. Okay, so that's kind of the idea behind this proof right here. If you have an odd vertex, then that is going to destroy the circuit there. So going back to the original problem, the original Königsberg problem, and if we look at that graph, we can see that this vertex over here has an odd degree, right? So D has an odd degree, so does B, right? So does this one, and so does C, right? And so that basically kills that off, and that's what Euler was able to figure out. Okay. The converse of that was proved about 100 years later by Heyerholzer, and that is if you have a pseudograph G that's connected and the degree of every vertex is even, then you are going to be able to find an Eulerian circuit in there. So that's the converse of the theorem that Euler proved. So that's an if and only if, right? A pseudograph G has an Eulerian circuit if and only if, right, it is connected and the degree of every vertex is even. All right. The proof of that uses this lemma here. If every vertex in a pseudograph G has a positive even degree, then any given vertex of G lies on some circuit of G. Okay, and again, that kind of falls back on that observation about with an even degree vertex, every time the circuit kind of comes in, it has an edge to leave. So the previous theorems about Eulerian circuits allow us to prove a couple of other theorems about decompositions. The first one here says that if a pseudograph G is regular of degree 4, then G has a decomposition into 2 factors. And so remember, regular of degree 4 means that every vertex has degree 4. And then a 2-factor, right, of a graph is a subgraph that has whose vertices all have degree 2. Okay, so here is an example of that. If you look, this graph here is regular of degree 4. Remember that the loop is counted twice, right? And so if you look at this, then we've got two factors, right? So we have this one with the edges colored blue, right? So you can see down here and this loop, right? And the red one as well, okay? And so remember, right, these, you might say, hey, wait a second, what about that loop, right? But remember, this loop is counted as being degree 2, right? So so therefore, this thing is a 2-factor, or this together with this is a 2-factor. So a 2-factor, right, would consist of some cycles, right, that are joined together. That's another way to look at it, right? And I have this cycle down here and this cycle down here for the blue graph, and then this red cycle as well. Okay. So the proof of this one, again, the idea behind this one is that you would start with an Eulerian circuit, and so then what you would do is just alternate the colors of the circuit itself. So if you think back to that example we did of the Eulerian circuit on this graph earlier, right? We went from A, so we colored that one red, and then used C, right, and colored that one blue. Then we went to D, so that's the next edge is colored red. Then we used edge H, color that blue. Then E, color that red. Then to vertex C using edge G, so that it's colored blue, and then alternate the colors back until we got here. So this graph had a Eulerian cycle, right? Well, we know that because all of the degrees are even, right, of the vertices. So you just start with the Eulerian circuit and then alternate the colors, and that will give this decomposition into 2 factors that you see here. Okay. So that's the idea behind that one. All right, and very similar to that is that a pseudograph G has a decomposition into cycles if and only if every vertex of G has even degree. So here you can see this one talks about cycles specifically. So here you can see the decomposition into those 3 cycles. I have the blue one from the previous example, the red one from the previous example, and since we're talking about cycles, I had to separate this loop off into its own one cycle, right? It's a cycle, the shortest possible one, right, with one edge, which is the loop. Okay, so in this case we have 3 cycles. So that's the difference between this theorem and the previous one. The previous one we said exactly two factors, right? Exactly 2 subgraphs, all of which whose vertices have degree 2. Here it is into cycles, so you can't do it with 2 cycles, right? In this case we had to do it with 3. So, but notice it doesn't say anything about the number of cycles you can decompose it into. All right, and so that is it on the decomposition ones. The next thing we need to talk about is an Eulerian trail. So an Eulerian trail in a pseudograph G is a trail that contains every edge and every vertex of G. Okay, so it has to go through every edge and every vertex. All right, and I have an example here. Let's take a look at it. And let's trace through it just to verify everything's correct here, right? So we start at A, and then we go to vertex B via edge A. Then from vertex B to vertex C using edge C, and then back. From C to B using edge D, then from vertex B to vertex A using edge B, then from vertex A to vertex D using edge E, vertex D to itself using the loop, then from vertex D to vertex C using edge F, like so. Okay. So that is an Eulerian trail, right? It's a trail. We can only use each edge one time. We did that. And this trail has to use every edge which we did, and every vertex, which we did. Okay. All right. So that's an Eulerian trail. All right, and so the next theorem that we're going to look at, right, is about Eulerian trails, right, and when a pseudograph has an Eulerian trail or not. So a pseudograph G has an Eulerian trail if and only if G is connected and has precisely two vertices of odd degree. All right, and so and what you'll find, right, is that the trail has to begin at one of the vertices of odd degree and end at the other one. That's how it's going to be, right? And that kind of goes back to what we were talking about with Eulerian circuits. With Eulerian circuits, every time you come into a vertex, then if you have an even degree, you can leave, right? But we said the problem is if you have any odd degree, that's going to mess that up because of the fact that there's going to be some time that the circuit comes in and you're going to have there's no edge to exit the vertex from. So with a trail, right, it's really similar to that. But if you have only two, right, vertices of odd degree, right, then if you start at one of those vertices of odd degree, right, then that means that you might never need to come back to that. If you do need to come back to it, then you have an even number of vertices left, right? And then that other degree of odd vertex with that one odd edge, that one leftover edge, you're going to use that to end the trail. And if you look back at the example that we did, right, there's no coincidence that you can see right here, vertex A had degree 3, vertex C had degree 3, and then vertices B and D both had degree 4, right? And so it's no coincidence that we started it at vertex A and ended at vertex C there. We essentially, that has to be done to make the Eulerian trail. You could there's others in here, right? But it's going to have to start and end at either A or C in some order. Either start at A or end at C, or start at C and end at A. Okay. So that's again the idea behind that one. Similar to the other decomposition theorems that we had, we have this decomposition into trails, and these are not Eulerian trails, but and this theorem generalizes the previous one. It says if G is connected pseudograph with precisely two H vertices of odd degree, where H is not 0, so you have two H vertices of odd degree, then there exists H trails, half the number, right, of the trails in G, such that each edge of G is in exactly one of these trails. Okay, and it says furthermore, fewer than H trails with this property cannot be found. All right, so you can see the example. They talk about this example in our book, but they didn't really draw it out. So I took the time to kind of draw it out so that you can see. And this is the tennis court graph, right? Because it looks like the lines on a tennis court, how they're painted, if you look from overhead. And so it would consist of all of these edges and all of these vertices. And so I colored the odd vertices black and the even vertices red. So here you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 odd vertices. Okay, so this theorem is saying that that you can find 6 trails in G such that every edge belongs to exactly one of those 6, right? Half the number of the odd vertices that you've got. And you can't do it with fewer than 6 trails either. All right, and so if what I did, and this is just a random thing that I did, I'm sure there's plenty of other ways to do this, but I started with this trail where the vertices were are where the edges are colored black here. So you can see I started here and just kind of wound my way up like so. Okay, and it ended there. All right, and then just started filling in with the other trails there. So there's one in red here, one in green here, one in blue, one in yellow, and one in pink. Okay. And so the idea behind this one, right? And one thing to notice is that these trails, right? They all begin and end at an odd vertex. Okay. If you look at all of the red vertices, those are the even ones. You'll see that no trail begin or ends at there. They have to go through those things. Okay. So the proof on this one, the idea behind this one is you have an even number of odd vertices, right? And so what you would do is connect, pair those things up, right? So put a new edge in from one of those to the other, right? And so pair those up. And when you pair those up, then what you have is a graph. That new graph, right, is going to be have every degree even, right? Every vertex will have even degree. So therefore, you have an Eulerian circuit in there, one that starts and ends at the same place. And then when you remove those edges in there, you're going to cut that circuit right up into H trails when you remove those edges that you added back in there. Okay, and so that's sort of the idea on that one. All right, so I think that is it on the overview of this, and that should be enough for you to get the homework done in here, and then I will go back and add in some details on those on the proofs, the formal proofs of these theorems that we talked about.